Well, and it's a great pleasure and honor to be here today. Let's go back nearly not quite half a century. It was in 1965-66. I was at the University of Maryland, College Park, on leave from the Max Planck Institute in Garching for plasma physics to Hans-Joachim. And I had to build a theater pinch for spectroscopic studies. In summer 1966, I was supposed to return to Germany, but two things happened. The pinch was running very well, and second, Alan Gabriel, then at Culham Laboratory, joined for a year, so I couldn't go back. This was a nice combination of experience. Alan had experience in plasma spectroscopy. I didn't, and I had experience in radial Thomson scattering, which delivered locally density and temperature. So it was a really great time which started. I think we both enjoyed it too much. We spent all day long in the lab, and as our lady stated, we had too much time, too much fun. We stayed too long. So we had two instruments. One was a grazing incident instrument, which Hans-Joachim acquired from Leon Haru. And this instrument, of course, was built for rockets, so we had to adapt it to the laboratory. Officially, this instrument was in the ocean by some bad luck with a rocket. And the second instrument was also a very simple Bragg crystal instrument from the Naval Research Laboratory. We also had to adapt it to a theater pinch operation. Now we decided we focus on helium-like ions, and we started studying the pinch, which we had diagnosed very well with Thomson scattering in the UV using the grazing incident instrument and in the X-ray region. In the following, I show one example, which was the scan of oxygen 6. Excuse me, oxygen gas. And here you see the resonance line and the intercombination line. And we were interested, of course, in the strong lines for diagnostic purposes. At that time, we observed weak lines here, and I did not comprehend what the weak lines meant. But Alan always said, when I go back to Culham, I study the weak lines. I said, okay. It didn't mean anything to me, but Alan was really excited about the weak lines. So, and one thing I have to point out, these were shots, several shots, so it was very tedious. We had to do many, many shots for a point and scan the whole spectrum. So you can imagine it took some time to get one spectrum. So what we did, we analyzed carbon-6, and we got collisional rates here for excitation of the resonance lines, exchange between singlet and triplet n equal 2. I think we discussed and worried about that quite a time. And we got the ionization from the ground state, from the time histories, and we had to include and also obtained rate coefficients for the ionization from the triplet states. Well, this we published in the first paper here. And of course, since we were interested in the diagnostics here, we did turn the results around and used it for the determination. This is a paper of the density and from the time history also the temperature for intercom from ratio resonance to intercombination line. Well, this ratio method was, of course, not the first idea. Here it was proposed by Griffin and Peacock the same year. Now, after return, Ellen returned for a short visit, and we met here in Dumbarton Oaks Garden, which is the right place for important visitors to take them. My wife has to apologize, she couldn't come today here. But there you look much younger, Ellen. Okay, when Ellen returned, the ratio method was applied to many plasmas, micropinches, and quite a number of papers on laser-produced plasmas, because it's the most convenient method to take a ratio here, because you don't need any calibration, which is the most problem in the UV region. And the lines are too close, so no calibration. And Alan, when he had returned, he extended, of course, the population densities, that you can use it for very low and very, very high densities. And you see here where the lines change in this region, you can apply the ratio method for helium-like ions. And this was extended in this paper here from carbon 5 to neon 9. Well, in the meantime, Alan had started his pioneering work, which also culminates now in the application to fusion studies. We heard a lot today already. Alan and Carol Jordan classified the laboratory lines, and he continued the studies we had done on helium-like lines. Now on a theater pinch he had built, and we find this paper. I jump the many contributions to solar physics because all the experts are in this room. His ideas and concepts came fully to bear again with the first spectra at the Princeton tokamak, which was published by Bitter and al. And we have seen already this graphs again. You see a very good fit here at PLT. And these spectra were obtained now with a one shot. So this was possible to the multi-wire proportional counters, which was really a great step forward instead of what we had to do a couple of years earlier, scan shot by shot. Now you got the whole spectra in one shot. You see very good fit, but of all the satellites line, Alan had classified. You see a very good fit, but when you talk to Bitter, he tells you they had to use a lot of fudge factors to fit the individual lines. So at that time, this was the state of the art. In the meantime, high-resolution spectra have obtained on many plasmas. On most fusion devices, you just can name all the tokamaks and other helical devices, and a respective system is now also prepared for ITER. Today, the knowledge by many contributors who are in the room here has been advanced so far that you don't need any more fudge factors to do a fit. You take the complete set of atomic data and you vary density and temperature, and you can fit it perfectly to, nearly perfectly to the spectrum. And I show in one spectrum by Marchuk from Textor Jülich. I show it because I was involved in this kind of work. And here you see the fit. And all the fits, as I say, are done, and there's only one discrepancy here, about a 5% on the intercombination line. So I think this is a really great advance. And here you see again the ratios, what you can do, what the satellites, what you can obtain. So this is the present state of art. Of course, now uses two-dimensional detectors and two-dimensional spectra by using spherically bent crystals. And here I see the one spectrum I got 2 days ago from the Jülich group. This is from the thesis of Schlummer. He has not submitted the thesis yet. And you see here the spectra two-dimensionally across the radius of a tokamak. Here is the center, and here is the boundary. And you see the resonance line does not change very much. But the C line, which is influenced by recombination strongly, changes very much from the center to the boundary of the plasma. And this means you have now terrific tools to study the diffusion in these tokamaks, which is very important. And recombination. And people also studied this spectra when you have beam heating, and you see the influence of charge exchange also on these lines. Okay, I think I close here. Thank you for your attention.